there, I'm Alejandro, and welcome back for day 148 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode Hard 2D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we got LeetCode Hard problem 312 burst balloons. You're given n balloons indexed from 0 to n-1. Each balloon is painted with a number on it represented by an array of nums. You're asked to burst all the balloons. If you burst the ith balloon, you will get nums of I times nums of I-1, nums of I plus 1 coins. If I-1 or I plus 1 goes out of bounds of the array, then treat it as if there is a balloon with a 1 painted on it. Return the maximum number of coins you can collect by bursting the balloons wisely. Oh, I see. This is going to be interesting. That is not the problem I expected here. Okay. I see. So really, for each index I, you have to be careful about the left and the right. Yeah, multiplying by 1 has no effect, basically. Can you go this in like groups of 3? Right? Like for example, if you pick index 0, it's nonsensical. Are all the balloon coins? Oh wait, they can be 0. Whoa, hold up. They can be 0? That's crazy. So bursting one might actually make things better? Wait, out of bounds of the array. Three times 5 times 8. Oh, I see. No, this is different than what I expected. Okay, 3 times 1 times 5. That's no longer possible. Oh, that's going to be an interesting problem, actually. Okay, yeah, I've never solved this problem before. Ever. Okay, yeah, I actually misunderstood the way this problem was going to work. Okay, so this 3 times 1 times 5, then 1 is gone, actually. So that's like almost like you split I to j into like I to x and y to j. It's like you take the case where maybe you multiply the values by x and y. Something like that. Yeah, this feels like a you split stuff problem, right? And it's gonna be, yeah, it's gonna be a 2D dynamic programming problem. So it's definitely gonna be something like, you know, def dp and I and a j. What's the time complex? Ooh, n is 300, so I am allowed to do O of n and work inside of this body, right? Here, if I whip out a terminal, right? If I do 300 to the power of 3, 10 to the power of 6. No, it does cut it close. It does cut it quite close, actually. But it's also j minus I, right? So really it's like, yeah, but this over 2 is still huge. Yeah, cubic might be a little tough, right? Yeah, it might be a little tough. Like what this makes me think is like, you know, for k in range, I come a j type of thing, kind of a problem. Let's think about it. If I pick one, right, I didn't know which one to burst from, right? So I try them all kind of a thing. If I burst one, the thing is I'm allowed to pick 5 and still have 3 in the equation. Yeah, you're literally bursting balloons. Yeah, this is gonna be weird. You're cutting in the middle of the array. You cut out index 1, so you want 0 to 0 and 2 onwards to be part of your solution. So it's either your next cut will be there and you just anticipate it beforehand. This is an interesting problem. Okay, yeah, this might be one of those where it's like I end up just thinking about it over time and so on. So like, yeah, this is good. It's one of those maybe where I just started. Yeah, I guess it's just I was on a streak. I was on a roll where it's like I solved this really quickly. I'm like, okay, why not one LeetCode hard before I go to sleep tonight? But yeah, this might be one where I have to think a little harder. So it might be wise to shower and so on, and maybe even come back tomorrow to keep trying it. But yeah, at least now I have an idea of what the problem is. This is actually kind of interesting. If I burst, I mean, if I burst that index j or I, it's obvious what I need to do. The question is, how do I split it, right? Because here I could do something like, first of all, we'll put an add cache. Here we'll do self.nums equal nums, return TP of 0, comma length of nums minus 1 probably. We'll do for gain range j plus 1. We are popping balloon and index k. Backtracking is not going to be necessary. I need to do this in a smart type of way. It's a DP problem. Yeah, this would be kind of hard to realize that this is actually a DP problem. We're told that it's a DP and it's a 2D DP problem. This one's going to be interesting, actually. Yeah, this is no coincidence. This makes me feel it's like, you have nums of I and you split in terms of left and right. Right? Yeah, I think it might be something like that, right? Coins is equal to none. Left is equal to nums of I Actually, yeah. Here we have I and j. Basically, if k is greater than I. k is greater than I. Oh, I'm getting a call from my friend. Oh, okay. My girlfriend is calling me, so give me literally just 1 second. Okay, I'm back. My girlfriend was just calling me to say goodnight, basically. Okay, we were right here. Alright, we are pumping balloon index k. Yep. That was 1, right? If things are in bounds. Then we're popping balloon index k. Yeah, so here we'll say left times mid times right. It's just I would love to. Is it something as simple as just a is equal to points plus self.dp of I comma k minus 1 plus self.dp of k plus 1 comma j type of thing? I greater equal to j. Assert I equals j. Return nums of I. Go of negative infinity. Res equals max of res in case. Right. Like I'm not like, world's most confident guy about this. Oh, am I out of Wi-Fi? Okay, well that is a bit of a rip. Okay, give me right in a second. I will fix my Wi-Fi in literally just 1 second. Okay, sorry about that. Since I'm on the guest Wi-Fi, I just have to refresh it every single 24 hours. So I guess like right now was the time. And yeah, okay, so here we get an invalid assertion. I equals j equals. Maybe this is like this. Oh yeah. Or maybe it's gonna be 1. Maybe here we should return 1 or something, because here we're already using a k or something. Wow, okay. Here maybe we just return 1. Yeah, okay. Okay, overestimate, underestimate. Yeah. We're gonna have to think about this a little harder. Yeah, it's not gonna be something as simple as this. Yeah, the hard part is about this is gonna be actually thinking about how to do this DP wise. If I choose to grab this 1 over here, how do I encode that for the rest of the problem? Right? It's either I continue merging from here. Right, there's really 3 cases, or like I do this one and then it's like I keep taking from one of those. It's like somehow I must know. Yeah, I can't try like the triangle permutation is obviously nonsense. That's the weird thing. It's gonna be like DP, but it's like if you have things like becoming 1s, it's like you can't really cache results. So you really have to like split this in subproblems like properly. Okay. Hmm. 5 burst the balloons here. Right? Choosing to burst the balloons here will allow me to do this guy over here. Like, how do I encode this? Wow. It's 2DTP. I want to see it. I mean, maybe it's like. I mean, it's 2DTP. It's not going to be like, 1D and O(n) work inside the body. Thing is, like, yeah, you can't decouple things. You choose to make a cut here, but they can still be integrated. Maybe it's like wherever I make the cut, I need to embody the possibility of merging things. Because I'm not really splitting the array, I'm removing an element. This is a very bizarre type of question. I'm bursting a balloon. Maybe it's like, yeah, it's ij, and I do ij to essentially denote the fact that I'm not allowed to burst the balloon at index k anymore, right? So maybe something like this is right, but it's how do I embody the logic of maybe I say it's like, hey, and indices I and j, the left of I and the right of I are ones, right? Guaranteed. Right? Yeah, so, yeah, for example, here k minus 1. To the right of it is k, which is a 1. To the left of this guy, it's a 1. So, yeah. I and j are real numbers. That's like, yeah, to the k, right, the max I can do is k, yeah. K minus 1, the max I can do there is like, yeah, multiply with k minus 1 to the right of it, which is a 1, and to the left of it, which will be a good value. Yeah. Oh, this is actually going to be nice. I guess it is just this, right? If I try to return something like that. Wait. If I is greater or equal to j. Alright, hold up. Assert I is less than or equal to j. Can I always make that assert? Well, that's a bloody problem. Case plus or equal to self.dp. Okay. Fine, we'll just do points. If k plus 1 less than or equal to j, points plus or equal to self.dp, k plus 1 comma j. Res equals max of res in case. And points, my bad. Not quite. Okay, wrong answer. Yeah, so here I'm generally allowing every single possible I. Res should always be equal to 1. Minimum. Okay, 66. Else points plus or equal to 1 maybe. Else points plus or equal to 1. No. Although we are getting case 2 correct, which is very promising. Yeah, I or j is fine. If you're less than I or greater than j, then you're not fine. Get val. Maybe here I should do I. I plus 1 to j. These are the easy cases. I less or equal to k minus 1 and k plus 1 less or equal to j. Right, and now these are underestimates. Case 1, burst balloons at I. We do that. Case 1 will be equal to 1 times nums of I times nums of I plus 1. Get val I minus 1 times get val of I times get val I plus 1. Plus self.dp. Here we chose to do index I. We ruined I plus 1 in the process. So here it's really just I plus, well, no, the I plus 1 is a 1. There's no incentive to do it anymore. So this Case 2, burst balloons at j. Case 2 is equal to something similar. J minus 1, j plus 1. Assert get val of I minus 1 equals 1. Assert get val of j plus 1 equals 1. And this should be, well, j has been bursted. J minus 1 will be a 1 because j was bursted. So we really should only go up to j minus 2 worst case from I. Now for the ones in the intermezzo, right? Then essentially you have an index I, or like an index k that you burst. If you burst at index k, then you've got index k is burst. K minus 1 is a 1, k plus 1 is a 1. So for the left hand side, you want to go to I. You want to go to I to k minus 2, don't you? Wait. So k minus 1. K minus 1 is a 1. It is no. K was burst. K was burst. So k minus 1 is a 1. So it is useless to burst k minus 1. Wait. First of all, here is equal to max of case 1, case 2. Print string, case 1 equals. That's fine, actually. Here we do that. Now it's like, okay, we've got nums from I plus 1, I plus 2, comma, comma, k minus 1, k plus 1. Here we'll do k plus 2 as well. As well as k minus 2, j minus 2, j minus 1, j. Now we're going to cut at this guy, right? So we're cutting at this guy. So boom, burst happens, right? So this guy becomes a 1. This guy becomes a 1. So if we choose this, right, this is a 1. This is also a 1. So really we only want to consider going up to k minus 2. So here we're going to do points is equal to here we can probably just do something like if I greater or equal to j, nums of I, if I equals j, L 0, so something like this. If I greater than j, return 0, maybe something like that is fine. Points plus or equal to and points plus or equal to self.dp k plus 2, comma j. Because k plus 1, you don't care about it. Wait. Am I doing this? Yeah, no. K plus 2 to the left of it, yeah. Multiplying by 1 is useless. It's like you don't want to go to a 1. You're just wasting potential if you're doing that. So there's a little bit of an aspect of greedy to this. Okay, how about something like this now? Wrong. Interesting. I thought I had it low-key. I mean, here we can try with all the plus 1s and see if I was wrong. I mean, yeah, we burst index j. We could still burst index j minus 1 if we really want to. This could be like a return 1. And then we make case 2 incorrect. So yeah, we've got case 1 incorrect. Okay, geez. But yeah, I am starting to get a feel for how this problem is gonna go. You have to essentially consider when you make a burst, the two things to the left are ones. Right, but yeah, no. This is wrong. If you allow for this, right, you cannot say I is valid. No. You gotta do a +2, -2. You definitely have to do things in this way. Right? No matter what, I can burst the balloon. Lambda index. This will be burst I. This will be burst J. Points is equal to burst K. Solve the dp from I to K -2 plus burst K. dp of K +2 from a J. I'm really surprised that this isn't that. Yeah, I'm really surprised that this isn't the right solution. Maybe it's like I can burst things from K +1. Right, it's the fact that K +1 is still a burstable balloon. And it might get stuff from the left. Yeah, I burst K, but it doesn't become a permanent 1. It actually gets rid of itself and makes this like that. Yeah, that's what I'm missing. Oh, that's annoying. Does this problem have any hints? Yeah, no. Yeah. It only becomes ones when it's the end of a wall. It's not like one of those where you just choose to burst. Yeah, you can burst anywhere you want in the middle. The hard part is realizing when you burst something, how do you encode that as the next DP step? You can code the permanent burst thing in here. I mean, at this point, I'm starting to get to like really slow time complexities anyways. Like I split that into 0 to 0 and 2 to 3. Somehow I need to allow option of still merging these two. Maybe I keep doing it until I'm done with one of the arrays. Yeah, this is tricky. I will probably just have to think about it. Yeah, I got a little, okay, for lack of a better word, I got a little cocky because I saw these 2 hards in a row. I was like, oh, yeah, let's just do another one before I go to bed. But yeah, there's definitely gonna be a thinker one. Oh, it doesn't look impossible. I feel like I'm getting to the right intuition of things. I'm going to have to figure out how I can essentially just combine results, right? Whether it's like, I keep essentially going through every single possible case of bursting in the middle, bursting in the middle, bursting in the middle. Right, for each K, I might have an additional 2 choices, right? Either like burst in the middle or don't. Right, there's definitely gonna be that aspect of I don't know which index to burst at, so try them all. But then it's how do you encode the remaining post-burst problem states? Because you have to allow one to talk to the other. Maybe that's where the 2 indices come in. Maybe it's like I is your starting index or whatever, and J is the starting index of the next thing you that. Maybe you always have 2 parts, right? You always have 2 parts of the array, right? Like here it's like this is the end of one, start of the other. At the beginning, maybe it's like ends at index n minus 1, starts at index n. It's just like, oh, it's nonsense. Could be something like that. Actually, that is probably something. That's probably on the right track itself. Maybe the 2D part might not necessarily be I and J being indices of nums. It could be. It could definitely be. I have to think. Can you have more than one section? You burst here. You burst here. You have some stuff on the left. You burst here. You have some stuff on the right. And then you can have stuff in the middle, stuff on the right, stuff on the left. But then it's like, yeah, if you're gonna do something to the right, then it's like that's its own bursting mechanic stuff. That could make a lot of sense. Maybe instead of indices, I representing a subarray cut of nums. Turn them into indices of their own respective sections. Solve the original problem. Just do a for loop every single possible cutting mission. initial cutting position. Bursting position. Or something like that. Actually, I kind of want to try something like this. Alright, here we'll call this. Something like that. Just at index 9. Burst at index j. Burst after index j, something like that, right? If I burst before index 9, then it's like, how do I deal with the second section, right? Like here I'm essentially creating a third section. To do, it's tricky. I'm essentially creating a third section. Yeah, I might have to revisit this problem. This is actually going to be a little bit tough. I'm just gonna have to think, right? It's almost midnight. I do have to work tomorrow, so I should probably stop here, take a shower, and just call it quits. But at least it's like it's gonna be like the binary search one. Maybe not in this extreme, but at least like I'll get a bit of time to think about it to myself and so on. Come back when I have an idea, maybe fail, maybe get it right. We'll see. And yeah, I think it's fair. Okay, it's nice. Like it's definitely a refreshing change instead of like oh I've seen this problem before. Oh, this problem is very easy and so on. Like struggling a little bit. So yeah, this problem is not immediately intuitive, even though I really love DP, and usually usually the hard part of DP is coming up with a recursive formula, right? Understanding it is a whole different ballgame. Like in the sense that that's usually much easier than actually coming it out from scratch. That's usually the hard part of DP, is coming up with it, right? Not actually understanding it. But yeah, I'll probably just give it a think during my own time and come back when I have a little bit of an idea, which may very well be tomorrow for me. So today is day 259. So when I come back, you'll see which day it is, and maybe it's after I did day 260. So who knows? We'll just have to see. So for me, it'll be a little bit of a while, but for you guys, I will be right back in literally just 1 second. Okay, hey there, I'm back. So, this is only a few days after I last continued. Right now it is Sunday night, around 8 p.m. My time, 8:05 p.m. My time. I've only eaten a banana, a Premier Protein shake, and a Kirkland Costco bar. So these bars are, let's see, how many calories? These are, and by the way, I do not like the way these guys taste, so once I'm done with them, so 190, so 190, so 190 calories, 190 calories, plus 160 for the Premier Protein shake, plus 100 calories for a singular banana. I'm at 450 calories, and it's 8 p.m. I am planning on feasting on a delicious shawarma chicken wrap from Aladdin's Gyro Cherry tonight on the University Avenue, but I figured I should try to give this a problem a try before I do so, in case I am able to finish it and go on and have a lovely shawarma. So I will admit I've been thinking about this problem, and quite frankly, I'm stuck in terms of ideas. Just it didn't take me 3-4 weeks, just like with the binary search one. The problem right over here, which is this binary search problem, the median of two sorted arrays. That one took me a long of a while before I looked at the hints. Oh, whoops! This is just a regular LeetCode page. Yeah, I just keep separate tabs and so on. Like this is my daily LeetCode challenge tab. This is my NeetCode current problem solving tab and so on. This is my GitHub tab, my NeetCode tab and so on. So I just keep things organized, and all the other tabs are for video uploadings. But yeah, so I've been thinking about this problem. And so it's 2DDP. So I realized, like, okay, so whatever I was doing before, yeah, not this stuff, but whatever, where it's like I divide this, where it's like I say, like, hey, you know what, if I'm going to choose to do a bursting at some index I, then it's like, yes. Wait, what was it? That one becomes 1 and its neighbors? Let me see again. We'll get numbers of I. Yeah, it's just that I'm allowed to burst that balloon. Yeah, nothing becomes a 1. It's just the size that becomes a 1, right? So that is the problem. Things do not necessarily become 1s. That's what makes this problem hard. When I burst a balloon, right? If I burst, right? If I have 1, 2, 3, 4, 5, right? And I choose to burst this 3, right? Then I get 2 times 3 times 4 in terms of value, right? But then, essentially, I can treat this as like, okay, I'm now getting rid of this 3, and I have this guy and this guy, right? But now it's like, I can't say that this is its own unique I to J problem, because it's like, if I burst a balloon here, it's affected by this guy over here, right? And it's like, imagine there were like, more elements here, right? If I had a 7 over here and I burst this guy, then this guy is like, gets split into this and so on. So it's like, I might have like, a very, non-constant amount of subarrays, which is very, very annoying to deal with. And so that's what I've been trying to think about, and essentially like, how do I go about this? And quite frankly, I'm generally stuck. And a lot of times with DP problems, it's like they're simple because they just follow a typical pattern, right? But whenever you have to deal with it, like maybe some new type of DP pattern, maybe this is not, but maybe it is. And so and I can't think of a solution at the top of my head. That's one of DP problems become hard, because the hard part about DP problems is often coming up with the algorithm, not understanding how an algorithm works, or like once you see the solutions, it's a pretty simple type of thing, or it's like not necessarily simple and so on, but usually the hard part of DP algorithms is coming up with them, right? Writing the recursive formula versus something like greedy. Greedy are very natural algorithms. You do the greediest possible thing you can, right? Like for example, here it would be like always pop the one that has the biggest value, or it's like look at all the indices and like calculate whichever one will give you the highest value of num_i minus 1, num_i and num_i plus 1, and use that one, right? The hard part of greedy is that, like, well, first of all, it might not always be correct, but if it is correct, you need to prove it, and that's the hard part of greedy algorithms, right? DP programs are the opposite. They're super easy to prove because they're recursive by nature. Like they prove themselves by nature, right? So writing proofs for DP algorithms is very, very well, not simple, but very straightforward. but coming up with them is the tough part. So what I was thinking is like, since I'm food deprived and I want to get through this problem, but I'm stuck and I don't want to think about it like, for 3, 4, or 5 weeks. And the genuine reason is that like, I'm so close to finish the 150. I just want to be done with it. So I'm going to make the leap and look at the hints. If I remember correctly, this problem doesn't have any hints, but we can always resort to, well, hopefully, I think NeetCode 150 has hints for every single problem, but here we can confirm or verify. And if this has no hints, I will be very sad, and I will probably end the recording and go get my shawarma wrap. But yeah, okay, so he does have some hints. So this is probably what I'm going to be looking at. So, I'm going to take a little bit of an L on this problem. I've been thinking about it, and yeah, it's not, I haven't been thinking it for forever. I've only been thinking about, like 3, 4, 5 days, like, half a week. But it's been on my mind, and I genuinely don't know how to get around this problem, right? Because it's like, whether I do, well, first of all, we know that it's a 2D DP problem, and even with O of N work in the body, where it's like I take an I, J, and I go through every single possible K, it's like, when I deal with those J and I's, it's like, how do I remember? It's like, okay, what's on the right and left and so on. And if like, if I keep track of like, oh, okay, this is the one that's actually there and so on, then it's like, I boil this down to be like 3D or 40 DP. And so then the time complexity becomes too low and so on. So it's just always a trade-off of like, okay, here's a solution that works, but it's way too slow. Or here's like, something that would be fast enough, but doesn't work. And it's just like, how do I get my way around things, right? And so, and what I mean is like, if you split, an array from I to J, it's like, okay, for J, if I split it at some index K, right? It's like, okay, I know that like, K's right one is, well, maybe I could keep track of a hash map, in terms of like, right and so on. But then it's like, you'll probably have conflicts just because you go recursively. Anyways, yeah, I'm having trouble with this problem, and I could think about it for a longer time. I could think about it for a couple weeks, but you know what? Let's get into the hints and just get a little bit of a push towards the right solution, because we might as well. I'm so close to the finish line, and I just want to get to that finish, baby. So you know what? Let's go ahead, starting with hint number 0, I suppose, which is recommended time and space complexity. Okay, so you should aim for a solution with O of n cubed time and O of n squared space, where n is the size of the input array. Okay, so it's nice to get a little confirmation, but yeah, I already suspected this. Just because it's like, with, O of n squared space, 2D DP problem, makes sense. And you're going to do O of n work in the body, makes sense, right? I'm guessing it's probably going to be some form of like, I to j splits, where you do like, you go through I to j and so on. Maybe it is as simple as just remembering it's like you made a split and... No, right? Because you do every K. That's not gonna work. But yeah, this okay. At least it's a nice confirmation that it's n cubed and not n squared. But it's like, I already couldn't come up with a solution in n cubed time, and other solutions I was thinking of that might work, but like are n to the 4th, n to the 5th. It's just not possible. It's too much, right? So just because the constraints here are 300, so n cubed was already kind of pushing it, but yeah, 300 to the power of 3 is this, 10 to the power of 6 is this. So yeah, it's already like 10 to the 7-ish to starts pushing it a little bit. So that's why I was maybe a little doubtful of an n cubed solution. But yeah, okay, at least we get that nice little confirmation. But nevertheless, let's get straight into it with hint number 1. Okay, try to simulate the process recursively by passing the array to the recursive function. Okay. At each step, iterate through the array, pop an element, and recursively apply... Whoa. Try to simulate the process recursively by passing the array to the recursive function. At each step, iterate through the array, pop an element, and recursively apply the same process. Wait, but this doesn't work. Wait, no. This is not what this is making me realize, but this is making me think of one thing. What if I set I and j to be illegal values to use. Dude, there's no way I wasn't thinking of this. Well, first I have to see if it works. What if? This is completely unrelated to what I'm thinking. It's like you know it's like he's telling me something I already know, but it's kind of like have you guys? Yeah, it's like it reminds me of that TED talk where you know, there's like 100 like super smart philosophers on an island, and they all have green eyes, or like a TEDx riddle, and it's like none of them can see that they have green eyes and so on. They cannot talk to each other, cannot give any cues to each other that they have green eyes, and at night they're allowed to go to the guard and say, "Can I leave the place?" And if they have green eyes, they can go, and if they don't have green eyes, then they're executed, right? And so all of the 100 philosophers or whatever they are can see all the other people, and they see they have green eyes, but they don't know if they have green eyes or not. Maybe they're the 1 out of 100 that doesn't have green eyes, so they're all too scared to leave the island, right? And then one time, like, you know, the guy in charge of the experiment tells this girl, like, okay, you can speak to them, but you can only say one sentence, and you cannot say anything that they don't know or that would help them figure it out, right? And so she's like, how can I say something that would help them figure it out, but, like, you know, wouldn't be obvious, and so that the guy in charge wouldn't know, right? And she ends up saying, like, okay, at least one of you have green eyes, right? And that's obvious truth, right? They all know that each of the other ones have there's at least one other guy with green eyes, right? And so, like, you know, the general's like, okay, well, if she didn't give any new information, all of them know that there's at least one other one with green eyes. But on the 100th night, they all end up leaving. And the guard's like, what the heck, how do they know, and so on. Which, you know, it might be a little tricky to understand, but, like, an easier example would be, like, you know, saying, like, at least 99 of you have green eyes, right? And then it's like, okay, well, each of them would know that there's 99 others with green eyes. So it's like, okay, guard might say, well, in that case, it's a little more sus, and he could have figured it out, but the concept of saying, like, at least one of you have green eyes is the same after 100 days as saying at least 99 of you have green eyes, because after one night, when they see that no one else left, that means, like, wait a minute. They didn't leave because they must have seen 99 other people, including me, with green eyes, thinking that maybe they're the 1 out of 100 that didn't have green eyes. But since they didn't leave, right, that means it's like, okay, they only see green eyes everywhere, which means that I must have green eyes and I can go, right, kind of a thing. This didn't tell me any new information, but it's making me think of a new idea. What if I set I and j to be completely off limits, right? But I could use it for my multiplications, right? And so here's, like, you know, you treat the ends as ones. So maybe we say nums is equal to 1 plus nums plus 1, right? I'm thinking something here. Okay. Let me cook. Underscore old. Here we'll say def max coins. Nums is equal to 1 plus nums plus 1. Here we'll say turn. We'll call this dp underscore new old. Okay, let's not get any conflicts here. 0, length of nums minus 1. Right. Wait, this I'm actually gonna be so dumb if this works. I'm gonna be so sad that I had to, like, you know, look at the hints, because I wouldn't have needed it if so. For now, we'll just do a cache. Here we'll say indices I and j are not allowed to be used. If I greater or equal to j, assert I equals j, I return 0. Right, I don't want to. Here we'll say k in range I plus 1 all the way up to j. You can pop that balloon. We'll say res is equal to 0. We'll say val is equal to here we'll say cell.nums equals nums. Nums equals cell.nums. 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 val is equal to nums of k minus 1 times nums of k times nums of k plus 1. Yep. Profit is equal to self.dp. So we popped k. We popped k. We popped k. So k's been popped, right? So it's like we say we have 1, 2, 3, 4, 5. This dude's been popped, right? So we say, hey yo, this and no, this doesn't work, right? Because again, 3 was popped out. So if I put this guy as the index and it's like, oh, this guy's not allowed. It's so annoying. Right, okay, yeah. I'm forgetting why this problem was hard again. Yeah, I'm not just gonna be able to do that to get away with, like, and like, I could put like, 4 is like, the value you're allowed to use on the right, and like I could keep track of its index. But if I do that for the right and for the left, then I have I and j as well as like 2 indices for like, what I can get on the right and left, which is just so annoying. No. Oh gosh. Okay, maybe we need a few more hints. All right. Try to simulate the process recursively by passing the array to the recursive function. At each step, iterate through the array, pop an element, and recursively apply the same process to the 2 subarrays on both sides of the popped element. But you can't do that. Like, how do you those 2 subarrays, you need to have them linked together. That's what I do not get. That is my problem with this problem. This approach is exponential. Can you think of a way to optimize it? Okay, hint 2. Instead of passing the array, we can pass the range of indices L and R that need to be processed. Okay, sure. We pad the input array with 1s on both sides for easier computation, but L and R represent the first and last indices of the original input array. Can you think of a reverse engineering approach for popping elements? We determine the results by considering each element as the last one to be popped in the current range. Oh, is he going to do this backwards? Wait. We determine the result by considering each element. My guy, this doesn't work. Then recursively solve the problems. This is exactly what my idea was, but this doesn't work because of that problem where you can't you have to link the arrays. What? Where I is the current element in the given range. Can you think of a way it? Wait, this helped me out literally 0. This didn't give me any new information. Yeah, bruh. Yeah, then recursively solve the problem. How? You need index I as the new guy. Bro, consider it as the last one. Nice. Unless it's like you propagate the multiplications or something. Whereas like when you pop the last one, you only have that value. Then as the second one you're about to pop, it's like, okay, that multiplication belonged to the previous pop. And now this doesn't help me with my problem. This is exactly the part at which I was stuck. Mate, come on, no. minus 1 we popped in the current range. For each element, we calculate its value by multiplying it with the elements at L minus 1. And R plus 1, then recursively. Yeah, well, this is exactly the part where I'm stuck. Like, you popped index I minus 1. Like, now can look at index I plus 1. Like, you're not limited here, man. Bro. Wait, L minus 1 and R plus... Wait, that's a huge change. Wait, this is the core part. L minus 1 and R plus 1. Oh my gosh. So that's the idea? If it's the last to be popped... and everything else is in here except this one index, then L minus 1 and R plus 1 outside of the current bounds is what's going to be remaining. There's no way that's the idea. It's so, like, simple, but, yeah, okay. Reverse engineering, literally. Holy crap, you have to literally... So I was every step of the way there, except at the end I have to tell myself, look at everything backwards. Okay, this is the part that I missed. He's not doing I minus 1 and I plus 1. He's doing L minus 1 and R plus 1, because he's saying everything from L to R will essentially be gone. So when you pop index I, everything from L to R is gone. So what's on your left and right? L minus 1 and R plus 1. That's nuts. It's super cool, but that's nuts. Oh my gosh. That's such a simple detail. Wow. Yeah, no wonder I wasn't on track, yeah. Like, I was trying to think, like, you know, either I blow up my DP size, make it 4D, which is just obviously not it. It's not going to even, like, pass in terms of time. I was having trouble already with... Yeah, so that's how he deals with it. Think of things in terms of last. Wow. That's cool. That's pretty darn cool. Gotta say so. Yeah. Let's restart. Self.nums is equal to nums. Nums is equal to 1 plus. Here actually we'll just do this. 1 plus 1. Lol. Actually, we'll just say nums. Turn cell.dp from the next 1 to n minus 1. Minus 2, actually. Yeah, this is more clear. Oh, that's so wow. Left val. Self.nums. Left val equals nums of right val is equal to nums of I plus 1. Left, right. Product. Left val. For now, we'll just, yeah. Here we'll say val is equal to left val times right val. Here we'll say I greater equal to j. Assert I equals j. Get val equal to lambda index. Get product for now we'll just make things suboptimal but understanding. Get product or get val. Val is equal to left val times right val. Get val is equal to lambda index val left times right val times nums of index. There we go. Nums of index times left times right time. Okay. If for k in range, assume index. Yeah, that's just so crazy. I had a j plus 1 actually. This should be a j plus 1. Myself. We assume k will be last balloon to get popped. For k in range, that's just such a crazy realization. Get val of k plus self.dp of I plus I k minus 1 because we just popped k. Alright. Plus self.dp of k plus 1 all the way up to j. Return max of this k in range I, j plus 1 pretty much. Wow. Really now? Oh yeah, because I'm gonna do this. So maybe I do I plus 1 to j. Wait, let me think about this. If I do I, I'm gonna have I minus 1 in here. I could just make this K, this K. Okay. Yeah, if I do I. Ah, yeah, because here I'll have I. Yeah, here I'll definitely need a K plus 1. Sure. No way. Fingers crossed. No way. That's actually crazy. And holy crap, yeah, we're at this standard deviation. Seems like there's maybe this is a bottom up. That's just wild. That's actually pretty wild. I'm not gonna lie. Wow. Wow. Maybe one thing we can do. Self.memo is equal to this. I, comma j in self.memo. And self.memo of I, comma j. Self.memo of I, comma j. It's res, return res. Maybe this makes things a little faster. Let's see. From 5 seconds to how much? Wow, that actually does not. Wow, and it brings us to this standard deviation. Wow, so this is people that use the cache decorator. Lol. Darn. Darn. Just wow. I'm like honestly speechless. Like, it's crazy how close. Like legitimately how close. Like I started thinking that I was not on the right track. Right? That I'm missing something and that I'm gonna have to do a complete problem reshift. So that's why I started like looking at the hints, because I'm like I'm probably going to a dead end, a trap, and I should be going some way how else. I didn't realize how close I was to this. Like, I shouldn't even say close, where it's like I did all the steps. The hardest step I didn't do, right? And it just feels like, yeah, even though you did 100 steps, that last step is harder than that previous 100 steps. Just realizing you have to think about this problem backward, because that's a twisted way of thinking, right? It's the last one you pop. You pretend everything in L to R is already popped. So obviously you multiply by the thing at the left of L and the right of R. Like that is crazy. I really like the way some people think sometimes. Wow. Generally, wow. Like that is pretty cool. It's just wow. I can't believe how close and how unbelievably stupidly far I was from. Like, even though I was right there, I wasn't gonna solve this for weeks or maybe even months. Like, I just need to get that idea of going backwards, and it's not it's not a typical pattern that you see in DP problems. So I'm kind of like in awe, like wow. Yeah, and it doesn't even feel that good, because it's like, yeah, wow, like that was what made this problem a LeetCode hard. Damn, that's pretty darn cool. I'm not gonna lie, that is pretty darn cool. I don't even know what to say. Like, dang. I'll still enjoy my beautiful shawarma, but like, yeah. And then now I feel I'm gonna think about this probably even more, than when I hadn't solved it. Like that's just nutty. That's a new way of looking at DP. Well, going about it backwards. Pretend it's the last one you look, not the first one. Like, because you know, like I'm always like in myself, like, oh no, case one I take this, I rob this home. Case two I don't rob this home, and it's just like, you know, it's about doing it right now. And it's like, no, pretend it's like the very last home you rob. And it's like, oh, what happens? Oh, well then all those homes would have been robbed. So this is like what a cool way of looking. It's definitely something. It's the first time I see this. I wouldn't be surprised if this is a common pattern in dynamic programming. That is pretty darn cool. Genuinely, legitimately impressive. Wow. Legitimately, wow. It's pretty darn cool. Pretty cool. Okay. Yeah, man. Okay. I guess that's it though. No, it's better to have it as a function. It just makes things more clear. Even if it doesn't get me that, yeah, like this is not going to be what gets me to this peak and so on. This is probably, you know, if you do the solution bottom up, which yeah, I don't even want to think about. It's probably not too complicated. Darn. I'm impressed. I'm generally left in shock. I'm very impressed by that solution and so on. It's just one tiny detail, but it unlocks everything. It makes you. It's what gets you from this problem is impossible, professor. I cannot do it in n cubed time. To yeah, obvious. like such a small detail makes you go from, oh, I need an n-fifth solution minimum, to well done. Just yeah, stuff like this is like what makes me think, like, you know, P is NP, maybe P equals NP. Oh, it should be the opposite, right? If people are this smart and we still haven't figured out, like, you know, P is NP, then it's like probably that P doesn't equal NP. And I know the main consensus about, you know, most people that actually think about this is like, you know, P doesn't equal NP. But darn, man, it would be pretty humiliating to prove that P equals NP though. Very humbling for the computer science world. Darn, that one little detail right there. Literally game-changing little detail. Okay. Well, nevertheless, as always in all my videos, they're a quick recap of isomorph solid problems. So for this one, this is like for me, this feels like very poetic, where it's just like, I was pretty much, like, think of this as like a problem that took 101 steps. Where it's like I solved the first 100 steps, and I was stuck in the last step, and I thought that, like, oh, I must be at step 0 actually, because maybe I went down the wrong track. But what's going on is that step 100 to step 101 is the hardest step, and is a step that's harder than 500 of the equivalent previous 100 steps. So what I mean by this is, like, I figured out that, like, you know, this is probably going to be, well, I knew it was going to be a 2D dynamic programming problem, and that I'm probably going to have to, like, split it into, like, subarrays I and j, where it's like, you know, if I do a burst at, like, you know, some index k between I and j, then essentially I split it into 2 subarrays where I must do some computations, and I loop through every single index k from I to j, and, like, you know, get which one gives me the best result. The problem that I was dealing mainly is if I have an array like this, and I choose to burst balloon 3, right? What I can do is, like, okay, I can say, like, you know, if this is my index I and this is my index j, I can loop it through every single index k in between I and j. right, and be like, okay, if I pop the balloon at over here, right, then essentially the value of this will be, okay, grab this guy, multiply by its two neighbors, right? So this 2 and 4, so that will be equal to 2 times 3 times 4. And then split into two subarrays, right? Then it's like, okay, now you're left with this guy and this guy because you popped this 3 in the middle. So, dp of 1 to 2 plus, dp of 4 to 5, right? Which is really just like, k plus 1 to j and I to k minus 1, right? Now the problem is, if I separate these two arrays into their own dp calls, the problem is if I want to burst the balloon at 2, right, I'm actually going to multiply a value of 1 times 2 times this 4 over here, right? This 1 to 2 really represents, right, really what this represents is nums from I to k minus 1 plus dp of nums from k plus 1 to j, right? And note that these guys might split into more subarrays, and so on. And somehow here, I need to keep track, like, okay, even though this goes to k minus 1, if I pop with this this guy, I'm actually going to multiply it with this value over here. But what if, like, this guy split into more, and so it's like, this guy's right value that I multiply with is actually like, right, if there's a bunch more elements, right, maybe it's like, some guy over here, and so on. And it's like, how do I keep track of all of this without, like, blowing up my dp array to keep track of, like, right and the left indices that you have to multiply by, and so on? Like, I'm gonna go crazy. It's like, how like do you truly separate this problem into two smaller subarray problems when it's like, they're tightly coupled with one another, right? Like, I know that if I burst this guy, it's going to be part of the value is going to be computed via another array index, which is part of, like, another subproblem, right? This is from I to k minus 1, but somehow I'm going to need the one at index k plus 1 as part of, like, the one of the possible values if I pop at this 2 over here, and so on. How do you deal with this, right? And so this is where I was completely stuck, and so I decided to look at the hints. And the hints have one crucial detail. And this is what I mean by the 100th to 101st step, which is we determine the result by considering each element as the last one popped in the current range. Work your way backwards from this problem. This is the one piece of detail that I was completely missing here. For each element, we calculate its value by multiplying with the elements at, well, we're popping index I here, right? We're going to split this problem to L to I minus 1, I plus 1 to R. This makes complete sense. We're not going to multiply the value at index I with the ones at index I minus 1 and I plus 1. We're going to multiply them with the indices at L minus 1 and R plus 1. What's going on here? L and R is basically my I and J. Here's what's going on. If you have a nums from I to J is equal to, let's grab one of the nums over here, right? Here we'll say 3, 1, 5, and 8. Right? Here's what's happening. We're going to say, hey, for each of these guys, what if this guy was the very last element to get popped, right? For example, if I say this 5 is the very last element to get popped, right? That means that it's like, okay, if I consider this guy to be the last one to be popped, what's going to be on this left and what's going to be on this right? Well, it's going to be whatever is to the right of J, right? That was not even in the original subarray, i.e., over here. And here we can consider, like, they say, if I minus 1 or I plus 1 goes out of bounds, and treat as if there is a balloon with a 1 painted on it. So here, really, we can pad with ones, right? Pad with ones, right? Now here, like, you're going to say, okay, I'm going to consider this guy to be the very last guy I ever pop. So if this is the last guy I ever pop, that means all the other elements inside of here do not exist except, for example, my 5. So if this guy was the last one I ever popped, then I would be multiplying this value by the two things on the exteriors, to the right of the original J and to the left of the original I, right? So 1 times 5 times 1, right? But you can see, like, if this problem becomes a little more crazy, right? If this is like, 1 and 5, right? And if I choose to split at this 8, right? Then essentially it's going to be like, okay, I consider this 8 to be the last one I popped, right? But then, since it's the last one I popped, when I recursively go to split the problem into this guy, right? And recursively split the problem into this guy, I can still consider my 8 over here well and alive, because I consider this 8 as the last one I popped. So when I'm working my way backwards and saying, like, I'm going to pop this one and multiply the ones on its left and right, I can still consider this 8 as well and alive for me to multiply my current 1's value with, because, again, 8 is the last one I pop, meaning, like, 1 might be my second last one I pop, and so on, which, holy crap, that is so unbelievably beautiful, I can't explain, and it's just something I would have not come up with. But that is a very pretty solution, because it's like, it perfectly works. It's so, it feels like there's a lot to consider and take in and so on, but like it works like beautifully. Like this is actually a really pretty solution. And so it's like by the fact that you pop 8 the last, when you compute its value, it's like you pretend everything else is gone, right? But then you can divide the problem into the two subarrays, right? Because this will be indices. So here you'll treat this as your official index 0 and your official index n-1, right? So it's like here you'll go from index nums from 1 to 3, right? And nums from 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 5 to 6, because that way if you pop the 1 at index 5, right? That's like you're going to multiply by whatever's at index 4 and index 6, because again, you assume that the 8 was the last guy you popped. So when you get to this guy to quote unquote pop it, you can look at the actually adjacent index value, because by the time you'll pop this guy will still have existed, which is just like, what a beautiful way of handling that problem of like, you're bursting things and it's like, how do I keep track of like, what guys are to my side and so on? Well, work backwards from the end upwards, right? Because when you work backwards from the last balloon pop to the top, it's like, that's so beautiful. I genuinely cannot exclaim it. Like it's so perfect. That is so perfect. I hope that that detail makes sense. It's just, it's not something I would have necessarily come up with, but it's like I can really appreciate a solution like that. That is really, really cool. It's just not a way that I would have, it's just not a type of way I would have thought about going about, a classical dynamic programming problem. But it's just another toolbox that I have in my window. So now it's like, if I'm intra-modifying an array, getting rid of elements, and somehow I need, towards the other arrays, that it's like, think of working from last to end. It's a very, very pretty solution, and a pattern that might appear in other problems, but it's just like, I'm very, very like, it makes me giddy, because this is a pretty gnarly cool solution. But nevertheless, in terms of coding, again, this is the thing with DP problems, coming up with a solution is the absolute hardest part, most often than not, more often than not. Actual writing and implementation or understanding of the solution is actually the easy part of DP. Which is actually like, the opposite of how greedy algorithms work, right? Greedy algorithms are very intuitive to come up with, but often wrong, or if they're right, very hard to prove, blah, blah, blah. But nevertheless, okay, so essentially what I do is, okay, first of all, I set nums to be equal to nums with 1s on both sides, right? It'll just make my life convenient, because then I'll go from index 1 and n-2, so that way it's like, if I ever want to say, okay, index 1, what's to the left of that? Index 0 will be this 1, and so on, so that way it's like, I can handle that, if things go out of bounds, pretend there's a balloon pin with 1 on it, so I just handle it that way. Oh, I set the nums is equal to nums, n is equal to length of nums, set the dp from index 1 to n-2, right? Because 0 and n-1 are reserved for those ones to essentially, which we've padded nums with, just for goodness sake, right? Just to make this problem simpler. Here we'll have def dp from I to j. Everything from I to j is allowed for us to pop. So here we'll say nums is equal to set the nums. Okay, let's get, we know that we're going to loop through every single index k, right? For every single k from I to j inclusive, right? So here I'm doing j plus 1 because it's j plus 1 not inclusive, but I. How is the problem going to be called? Well, we're gonna pop index k, right? But index k will be the last balloon we pop. So if we consider all the elements from I to j inclusive, right, which is what we're considering in our current DP call, we're going to loop through every single index k from I to j inclusive, and we say, okay, what if we popped index k last? If we popped index k last, then it'll be nums of k times nums of I minus 1, because everything from I to j except index k are all gone. So what's to the left of index k will be index I minus 1, and what's to the right of k will be index j plus 1. So let's first of all compute the values of nums of I minus 1 and nums of j plus 1. And here let's multiply them together for the sake. And we'll have a get value function, which given an index k, or index here, we'll get nums of index, and we'll multiply it by nums of I minus 1 and nums of j plus 1, right? So we just have a helper function just to make things a little faster. Here we have a base case. If I is greater or equal to j, then there's two possible cases, right? If I is greater than j and so on, that we don't have an array to deal with, right? For example, if I say, nums is equal to 1, 2, 3, 4, 5, right? And I do nums from 2 to 1, right? Nums from 2 to 1, it's like, an empty array, like, I is greater than j, there's nothing for us to deal with, so I just return 0 for a total sum of 0, right? Otherwise, if I is equal to j, that means it's like, okay, I can pop index I, and again, I'm going to have the value be the number at index I times, the number at index I minus 1 and the number at index j plus 1 all multiplied together. So here's just get val of index I, because I wrote that helper function to help me do that, right? Otherwise, we'll go through every single possible index k from I to j inclusive, and how will we compute the value? We'll get the value of popping index k last, right? Remember, index k times the numbers at index I minus 1 and j plus 1, because we assume that it's the last one. So everything from index I to j has already been burst except for index k. So that's why we're getting the value times I minus 1 and j plus 1. And then we recursively divide into the two arrays, right? We do sell the dp from I to k minus 1 and sell the dp of k plus 1 to j. But here we don't have to worry, right? Because for k plus 1, right, we'll say, oh, to the left of it is k. But here we're saying, index k was the last one we popped, so it should legally exist when we go into this recursive call and be like, okay, I want to add the value, multiply my value at index k with k plus 1 with the one right before it, which is k plus 1 minus 1 is equal to k. Because, again, since this is the last one we pop, whatever we do in here will have come before the popping of this index k. So it's like, this guy can look at this, multiply by the value at literal index k and so on, which again is what makes this problem so beautiful, right? And I hope that little detail makes sense. But yeah, that is generally a beautiful way to solve the problem. It's like it shouldn't work, and it's like this problem. It's almost like this problem was made for this type of solution. It is actually pretty crazy. And again, yeah, we do this for every single k from I to j plus 1. We do this for every single k, and we just obviously return whichever one gave us the maximum total amount of coins, right? And that's pretty much it. And obviously the original problem we solved is from index 1 to n minus 2, because index 0 and n minus 1 are just these ones that we added for padding for the sake of solving the original problem, right? And that is literally pretty much it. I'm going to delete these comments over here. And here we can submit one more time. And our solution is about 5 seconds long, right? So like about 5,000 milliseconds. It's in one of the standard deviation peaks, which we'll see right now in a bit. So yeah, it's like inside of this standard deviation peak. I'm guessing this one is probably if people are doing it like, bottom up instead of top down. But, in terms of asymptotic complexity, it doesn't really change the name of the game that much. But otherwise, that is pretty much it for this video. If you did find it useful, enjoyable, in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, my friend. Bye-bye. Sorry, just one more thing before I leave here. I just want to, I forgot, as always, to come over here and, first of all, just check off the fact that I did this problem. So there we go, bada bing, bada boom. But more importantly, one thing I want to do is just because, even though I didn't solve this myself, again, I know I've said this a million times in this video. This is such a beautiful solution, and like it's really making me think. I feel like I unlocked a new tool that probably will almost never come, but it's just like a really cool way of approaching a problem. So I'm gonna give this my second star so far inside of the entire NeetCode 150, where it's like, yeah, even though I wasn't able to solve this problem, what an unbelievably cool solution. It's just one tiny little detail of going backwards and so on, but it's like it works so perfectly that like I generally really like the solution. So the only other star I gave, I think it's either in graphs or advanced graphs. Okay, yeah, so not here. Yeah, was this one, minimum cost to connect all points, just because it's like I believe it required like Prim's or Kruskal's algorithm to basically build an MST. Yeah, sorry about that. Yeah, but I have VS Code just because that's where I keep my schedule. Where like if you look in the comments below, there's like a little schedule of like all the NeetCode 150 problems and so on. And so I just have my file that I open VS Code and edit there and so on. So yeah, but yeah, I need to eventually update that thing. But yeah, this is the. This required like Prim's or Kruskal's algorithm, and I forgot how to write those algorithms, and I don't even think I ever wrote those algorithms, and so I was like learning how to write it from scratch in there, and so like I was like, whoa, no way, I was able to figure it out. That's such a cool. So this one made me really happy as well. But all the other problems I have not given a star, so it's just been minimum cost to connect all points, and now burst balloons, like what an amazingly cool solution. So I just want to let that out of the bag right before I end the video. And yeah, obviously to check off the fact that we did the problem, because now we're at 148 out of 150, baby. We only got 2 more problems left. That feels absolutely incredible. But otherwise, as before, that's pretty much it for this video. I hope you found it useful, enjoyable, or entertaining, or informative in any way, shape, or form. And so again, if you did enjoy this video, I would appreciate if you left a like or comments. But otherwise, generally for real this time, I will catch you in the next video. So until then, ciao, ciao, my friend. Bye-bye.